For thousands of years, humanity could see only one face of the moon. But what's hiding on the other side? Welcome to This Explainer. Today, we're diving into a real cosmic detective story to answer a question that's honestly baffled us since the dawn of time. Why can't we see the far side of the moon?
You know, whenever you look up at the night sky, whether you've got a massive high-powered telescope or you're just looking with your own two eyes, you are literally always greeted by the exact same lunar features. The same craters, the exact same dark plains of cooled lava. It really begs the question, right? What exactly is out of our sight? And more importantly, why are we restricted to just this one single view?
Well, to understand why one side is perpetually hidden from us, we first have to tackle a huge misconception. People look up at that fixed face and logically ask, does the moon actually rotate at all? It's super easy to assume our moon is just sitting there, just motionless in space, anchored in the sky like a painted backdrop.
But the resounding answer to that is yes, absolutely. The moon rotates. It is definitely not some frozen, stagnant rock. It's actually in constant motion, spinning around its own axis as it travels through space. Now, the really surprising part is how it rotates, and how that spin perfectly lines up with its journey around our planet.
And that brings us to the scientific heart of the whole mystery: synchronous tidal locking. Basically, this is when an orbiting body's rotation period perfectly matches its orbital period around its partner. So how did this happen? Well, Earth's immense gravitational pull heavily affects the moon. Over a really, really long time, billions of years actually, the tidal forces generated by Earth's gravity changed the moon's rotational energy. It basically acted like a giant gravitational brake, slowing the moon's spin down until it became perfectly synced up with its orbit.
Let's actually look at the numbers to see how this plays out with what we call the 27-day rule. The moon takes exactly 27 Earth days to complete one full orbit around our planet. But here's the kicker. At the exact same time, it takes exactly 27 Earth days to complete one full rotation on its own axis. Because these two motions take the literal exact same amount of time, the physics lock its near side to our perspective here on Earth.
Think of it like this brilliantly simple analogy. Imagine walking in a circle around a friend, but you want to always maintain eye contact with them. To keep your face pointing at them the entire time you're walking around them, your body has technically rotated one full time by the end of that circle. If you didn't rotate, eventually your side and then your back would be facing your friend. So the crucial equation to remember here is super straightforward. The moon rotates once on its axis, plus the moon completes one orbit around Earth in that exact same time frame, equals the exact same lunar hemisphere remaining directed toward Earth. This is the core scientific explanation for why we only ever see the near side. It's not stuck, it's just moving in perfect, synchronous harmony with us. Now, since we've established that the moon is tidally locked, you might think this tight gravitational bond means we're strictly limited to seeing exactly 50% of the lunar surface. But the reality? It's actually slightly more flexible, and honestly a lot more dynamic than that. This introduces a really fascinating phenomenon called libration. Basically, libration is an apparent wobbling motion of the moon as we view it from Earth. Because of this visual effect, observers here can actually peek slightly around the moon's edges. Now, to be clear, this doesn't mean the moon is suddenly unlocking from Earth's gravity or breaking its tidal lock. No, it's entirely a consequence of the moon's orbital geometry and how it looks from our vantage point. So why exactly does it wobble? Well, first off, the moon's orbit is not a perfect circle. It's actually elliptical. That means its distance from Earth changes, and so does its orbital speed. It literally moves faster when it's closer to us and slower when it's farther away. But its rotation speed on its axis remains totally constant. This slight mismatch between a changing orbital speed and a constant rotational speed lets us peek just a little bit more around the eastern and western edges. Add in a 5-degree tilt to the orbit, which lets us nod past the northern and southern poles. And over time, we actually get to see a bit more than half of the moon's total surface. But what's truly fascinating is what we actually find when we look at that hidden side. The far side isn't just a simple mirror image of the side we see every night. The NASA data reveals striking physical differences. Just look at the crust thickness, for instance. The crust on the near side is about 25 miles thick, but on the far side, it reaches up to 37 miles thick. Scientists are incredibly interested in studying the far side precisely because of major differences like this, which hold massive clues to the early formation of our solar system. And honestly, the fact that we even know about this thicker crust is a total triumph of modern science. Because for thousands of years, humans on Earth could not directly see the lunar far side.
It was an absolute mystery right up until 1959, when the Soviet spacecraft Luna 3 flew past and captured humanity's very first photographic glimpse of it. Today, robotic spacecraft and orbital imaging from NASA have mapped it in stunning high resolution. And with modern missions like Artemis 2, humans are actually flying around it to study it as this pristinely preserved 4.5 billion-year-old time capsule.
Now, with all this talk about a hidden, mysterious hemisphere, we have to pause for a second. We need to aggressively debunk one of the most persistent pop culture myths in all of astronomy. People often wonder, because we can't see it, is the far side always dark? The answer to that is a definitive, absolute no. The term dark side of the moon is completely scientifically inaccurate. The correct, factual term is the far side of the moon. The word far simply describes its geographical relationship to Earth. It's just the side facing away from us. It has literally nothing to do with its exposure to sunlight. The reality here is that the far side receives just as much sunlight as the near side. You have to remember, the moon is always half lit by the sun, just like Earth. As the moon goes through its phases, the light shifts. So during a new moon phase, when the side facing Earth is completely dark to us, the far side of the moon is actually fully illuminated by the sun. It's experiencing its own daytime. And to further prove that our moon is a dynamic part of the solar system, let's look at this measurement: 1 inch. While the moon's rotation is perfectly locked to its orbit, its actual distance from us is not totally fixed. NASA measurements show that the moon is slowly moving away from Earth, getting about 1 inch farther away every single year. This gradual outward drift is connected to the gravitational interplay between the moon and Earth's ocean tides. So let's bring all of this together. Far from being some frozen, motionless rock stuck in the sky, the moon is an incredibly dynamic cosmic system. It's constantly rotating on its axis, it's in a continuous orbit around Earth, it experiences libration, giving us that apparent wobble, and it's gradually drifting outward into the cosmos by an inch a year. The only reason we don't see its far side is because of the elegant physics of synchronous tidal walking, not because it isn't moving. We've explored the mechanics of its orbit, we've mapped its thick, rugged crust, and we've definitively debunked the dark side myth. But as humanity prepares to return to the lunar surface, and as the moon continues its journey an inch at a time further into space, you really have to wonder, what other hidden cosmic evidence is waiting for us just out of sight? Thanks for joining me on this explainer, and keep looking up.